join us. Welcome everyone. You are joining us for Engineering Tunable Multi-Wavelength LED Illumination for Biomedical and Life Science Instrumentation, presented by Innovations in Optics and hosted by Photonics Media. Today's speaker is Thomas Brucolacchio, the CEO/CTO and co-founder of Innovations in Optics, where he directs the development of high-radiance solid-state illumination systems for biomedical, solar, semiconductor, and industrial instrumentation. Also joining us is Karen Allardyce, a business development and applications engineer at Innovations in Optics, where she is responsible for guiding market development and working with OEM manufacturers, research laboratories, and technology companies to integrate high brightness LED illumination systems into advanced instrumentation. A quick note, feel free to ask questions in the chat box at any time. If you experience technical issues, try logging out and back in. You'll receive a link to the webinar recording in your inbox after the session. With that, let's welcome Thomas and Karen.
Thank you, Haley.
Thank you, Haley. Well, good morning, everyone. Good afternoon or good evening, wherever you are in the world. And thank you so much for joining us. Over the last decades, biomedical imaging has progressed from simple visualization toward increasingly sophisticated methods for detecting, measuring, and analyzing biological information. Whether we're performing fluorescence imaging, PCR analysis, endoscopy, microscopy, or multispectral imaging, the quality of the illumination is key. It determines the quality of the information we can extract. At the same time, illumination technology itself has undergone a major transformation. Advances in LEDs, VCSELs, optical design, thermal management, and electronic control have created new opportunities for compact, highly controllable illumination systems that were simply not possible with conventional lamp-based approaches. So today, Tom and I will examine some of the engineering principles behind these systems and discuss how they are being applied across a wide range of biomedical and life science instruments. Here's a quick roadmap for today's discussion. We'll begin by looking at the types of biomedical applications that rely on advanced illumination and the performance requirements they create. Next, we'll review several engineering fundamentals that influence illumination system performance, including optical coupling, radiance, thermal stability, spectral control, and electronic drive architecture. We'll then examine how those principles are applied in real biomedical instruments, including fluorescence imaging systems, PCR instrumentation, multispectral imaging platforms, and endoscopic illumination systems. And then finally, we'll discuss emerging trends in biomedical imaging and where the future opportunities may exist for spectrally programmable solid-state illumination technologies. Much of what we'll discuss today comes from practical illumination challenges we have encountered while developing biomedical instrumentation. So I'll begin with a brief introduction to Innovations in Optics. Innovations in Optics, otherwise known as IOI, was founded in 1993. And we focus on the development of high-power solid-state illumination systems for demanding industrial, biomedical, analytical, and scientific applications. For over 3 decades, we've developed a broad portfolio of technologies involving LEDs, VCSELs, optical coupling, electronics, thermal management systems, high-radiance illumination platforms in general. We are located just outside of Boston, easy access. Please come visit us. And we have all of our engineering team, R&D, from optical to electrical and mechanical on site, sales and marketing team, high power, high volume production, and clean room, all housed in one convenient location. So before looking at specific applications, it's useful to step back and consider the role illumination plays within a biomedical instrument. The illumination system has a direct impact on the quality and reliability of the information being collected. Image quality depends on delivering sufficient light to the target while maintaining uniformity, contrast, and signal-to-noise ratio. The spectral content of the light influences what biological features can be visualized, measured, or distinguished. Whether we're performing fluorescence imaging, PCR analysis, tissue characterization, or surgical visualization, wavelength selection can significantly affect measurement accuracy and diagnostic performance. Stability is equally important. Variations in optical output, wavelength, or illumination uniformity can affect repeatability, calibration, and long-term measurement consistency. For many biomedical systems, illumination becomes part of the measurement process itself rather than simply providing visibility. As biomedical imaging continues to evolve toward more analytical and quantitative techniques, illumination increasingly becomes an engineered subsystem that directly influences overall performance. To see how these requirements emerge in practice, let's take a look at several biomedical and life science applications that rely on advanced illumination technologies. Biomedical illumination systems are used across a remarkably broad range of instruments and imaging modalities. In some applications, illumination is used primarily to generate analytical information, such as fluorescence measurements in PCR systems, protein analysis in Western blot imaging, or quantitative measurements in spectroscopy and molecular diagnostics. In other cases, illumination supports direct visualization. Examples include endoscopy, surgical imaging, microscopy, ophthalmology, and a variety of clinical imaging systems where image quality and contrast are critical. Although these applications serve very different purposes, they all depend on the ability to deliver the appropriate light to the target in a controlled and, importantly, repeatable manner. As biomedical instruments continue to incorporate more imaging and analytical capabilities, these demands placed on illumination systems continue to grow. Specifically, LED illuminators enable analysis and identification of microbial pathogens, not only in clinical settings, but also in the food industry. IOI light engines were used during COVID to detect and study the virus. Surgeons operate with clarity as blood vessels or cancer cells are identified under specific wavelengths. Tissue can be seen despite a pool of blood. LEDs in the UV regions are used for dental curing, and high power white allows visualization of the eye and also aids in endoscopy and colonoscopy. Regardless of the application, though, several performance requirements appear repeatedly across biomedical illumination systems. Many instruments require multiple wavelengths to support fluorescence excitation, spectral measurements, contrast enhancement, or multimodal imaging approaches. Radiance and efficient optical coupling are frequently important because light must often be delivered through fibers, small apertures, compact optical systems, or highly constrained instrument geometries. Uniformity and long-term stability are also essential. Consistent illumination improves measurement repeatability, calibration accuracy, image quality, and overall system reliability. Finally, biomedical instruments often operate under strict constraints related to size, weight, power consumption, and thermal management, making compact and efficient illumination architectures highly desirable. Balancing all of these requirements creates significant engineering challenges. So here's one: efficiently delivering photons into small optical systems is a central engineering challenge in biomedical illumination. Many biomedical systems use fiber bundles, endoscopes, or compact optical geometries, where efficiently delivering light becomes much more difficult than simply generating it. In these applications, total power alone is often not enough. What really matters is how efficiently photons can be collected, concentrated, and then finally delivered into the usable optical aperture. Many systems also use high numerical aperture fibers, often around Na.66 in endoscopic illumination, to maximize light collection efficiency. But even with higher Na acceptance, preserving radiance and minimizing optical losses through a constrained optical geometry remains challenging. This becomes especially important in fluorescence imaging, where excitation intensity directly affects signal strength and measurement sensitivity. As a result, the optical system design, including collection optics, homogenization, and coupling efficiency, plays a major role in overall system performance. Even after efficiently delivering photons, biomedical systems still face another major challenge. Different applications often require fundamentally different spectral characteristics. Systems often need to support both broadband white light for visualization, for example, endoscopic viewing, surgery, microscopy, and narrowband spectrally controlled light for analytical measurements. For example, fluorescence excitation, PCR, tissue differentiation, hemoglobin contrast, ICG imaging. Historically, this required filters, multiple sources, and mechanical switching. In applications like endoscopy and colonoscopy, physicians need high CRI white light for natural tissue visualization, but they may also need narrowband wavelengths for fluorescence imaging, hemoglobin contrast enhancement, or molecular diagnostics. Historically, these functions often required separate light sources or mechanical filtering system. However, modern multi-channel LED architectures now allow these modes to be combined with a single electronically controlled illumination platform. For example, spectral illumination can reveal features hidden under white light. To your right, you'll see a figure that shows a colonoscopy image of a colorectal polyp adenoma. The different panels show the same lesion viewed with different spectral imaging techniques. The enhanced imaging modes increase the contrast between abnormal tissue and the surrounding healthy mucosa, improving lesion visibility. LEDs are not cool devices at high radiance. Temperature affects both optical output power, wavelength, and lifetime. Thus, providing temporal stability is critical in measurement systems. As LED junction temperature, for example, increases, optical power decreases, and wavelength shifts, and long-term degradation can accelerate. For example, the graph that you see there is an LED at 940 nanometers, and it shows a significant shift of 20 nanometers as the board temperature increases. So thermal management is critical. In biomedical systems, these effects directly impact performance. For example, in fluorescence imaging or PCR, wavelength drift can affect excitation efficiency and measurement repeatability. In white light imaging systems, such as endoscopy, thermal drift can also affect color temperature and color rendering. As a result, thermal design becomes a full system level problem involving optics, packaging, PCB design, heat spreading, airflow, and electronic control. These stability requirements become more demanding even in multi-channel illumination systems, where multiple independently controlled wavelength bands operate together within the same optical platform. Maintaining consistent spectral balance across all channels over time can be challenging as thermal conditions change during operation. As a result, temporal stability becomes closely tied to the thermal design, active feedback control, airflow management, and system-level thermal regulation, rather than simply maximizing optical power alone. In high-power systems, TEC stabilization can help maintain more consistent junction temperatures, spectral balance, and multimodal imaging repeatability across changing operating conditions. The thermal analysis shown here illustrates how LEDs, TECs, heat sinks, and airflow and ambient conditions must all be considered together within modern biomedical illumination system design. Traditional sources like xenon and arc lamps can be very powerful, and they have their place, but they lack flexibility and efficiency. They have several challenges and limitations, including a short life. Intensity continues to degrade, and bulbs must be replaced frequently. So the cost of operation is high with maintenance and downtime. Arc lamps are temporarily unstable, which creates inaccuracies in diagnostics, and they require warm-up and cool-down time. Mercury and ozone are harmful to the environment. Mechanical shutters and filters are required, which impedes quick wavelength selection and ease of operation. These optical, spectral, and thermal challenges and lamp limitations are what drove the development of modern multi-channel LED illumination architectures. LEDs introduced reliability and control, and they enabled entirely new illumination systems. There are now numerous LED wavelength and power bands available, from lower UV through SWIR, and improvements in optical power output and reliability continue. And in addition, VCSELs offer an alternative as well with narrowband features and higher power that can be advantageous for some applications. Implementing them in manufacturing is very similar to LEDs, and wavelengths that are available now include red through near IR, but they're continuing to develop more wavelengths. Modern biomedical instruments increasingly require multiple wavelengths, higher output power, programmable illumination modes within a single compact system. Multi-dye light engines allow different wavelength channels to be integrated together and independently controlled electronically. LED systems provide rapid spectral switching, synchronized pulsing, and programmable spectral output. This enables functions such as fluorescence, excitation, white light imaging, narrowband contrast enhancement, and multimodal imaging within the same illumination platform. At the same time, integrating many emitters into a compact optical system introduces new engineering challenges involving thermal management, optical homogenization, radiance preservation, and electronic control. As a result, the performance of these systems depends heavily on how the complete illumination system is engineered. Whether it's single or multi-wavelength, the photons need to be collected efficiently and well controlled. Often, light must be collected from multiple LEDs, conserve radiance, homogenize the output, and efficiently couple the light into fibers or constrained optical geometries. Étendue becomes an important consideration because it fundamentally limits how tightly light can be concentrated while maximizing optical throughput. As a result, non-imaging optics, such as compound parabolic concentrators and tapered optics shown here, are homogenizing structures, and they're often used to improve collection efficiency and maintain usable radiance throughout the optical system. However, at IOI, we like to say we are breaking the étendue barrier with a patented approach. Actually, we recover and recycle the photons that would otherwise be lost, thus increasing the optical throughput. These diagrams illustrate two different recycling approaches involving reflective field stops and reflective aperture stops. The light is reflected off the field or aperture stop back onto the LED dye, which are also reflective. Thus, the light is redirected back into the optical system to improve optical throughput and partially overcome some of the practical limitations associated with étendue. Optical recycling can significantly improve usable throughput depending on reflectivity and the system geometry, of course. The effectiveness of optical recycling depends strongly on factors such as reflector efficiency, wavelength, and the degree of étendue constraint within the system. On the left is an example of measured spectral reflectivity in the UVA region for several reflective materials used in recycling structures. On the right, the performance curves illustrate how increasing reflective efficiency can substantially improve the percentage of usable light delivered above the étendue limited matched LED area. As reflector efficiency improves, a greater fraction of rejected photons can be redirected back into the system, and ultimately they contribute to the useful optical output. These approaches become especially valuable in compact, high radiance illumination systems where maximizing optical throughput is critical. So, achieving high performance biomedical illumination requires coordinated optimization of optical, thermal, mechanical, and electronic systems. High radiance biomedical illumination systems require much more than high power emitters alone. The complete illumination architecture must integrate optical collection, thermal stabilization, packaging precision, and electronic control into a compact and manufacturable system. In this example here, the close-packed multi-dye LED array is integrated with non-imaging optical structures such as tapered optics and compound parabolic concentrators. They're designed to efficiently transfer the light through the system while maintaining high usable brightness. Thermal management also becomes critical because high current density and compact packaging can strongly influence wavelength stability, output power, and long-term reliability. As biomedical systems continue evolving toward higher power density, multimodal operation, and smaller form factors, this type of tightly integrated optical and thermal system becomes increasingly important. Modern biomedical systems require illumination that can adapt dynamically to different imaging and diagnostic modes as well. So how do we effectively control what photons are delivered to a target? One of the major advantages of modern LED illumination systems is the ability to electronically control spectral output in ways that were difficult or impractical with traditional lamp-based systems. Instead of relying on fixed broadband illumination combined with mechanical filters or shutters, multi-channel LED systems can independently control specific wavelength bands electronically and in real time. So this allows illumination systems to support both broadband white light imaging and narrowband analytical modes within the same platform. In biomedical applications, different wavelengths can be optimized for different functions, such as fluorescent excitation, or hemoglobin contrast enhancement, tissue differentiation, or molecular diagnostics. Spectral programming also enables rapid switching between the modes, synchronized imaging sequences, and multimodal operation without requiring multiple independent light sources. As a result, spectral control is an important feature of modern biomedical illumination system design. Achieving this level of spectral flexibility requires precise independent control of multiple wavelength channels. Medical applications require precision, accuracy, and repeatability, and properly engineered LED illumination systems can provide these capabilities. Electronic drive architecture plays a central role in the lifetime, stability, timing, and modulation behavior of LED illumination systems. Unlike traditional lamp-based systems, individual LED channels can be electronically adjusted with precise control of current, timing, pulsing, and triggering. Because LED current varies exponentially with voltage, constant current sources are commonly used to avoid overdriving the emitters while maintaining stable optical output. High-speed modulation also enables pulsed operation, synchronized imaging, and rapid transitions between illumination modes. LED response times are extremely fast, in fact, typically on the order of nanoseconds, which enables precise synchronization with detectors and high-speed imaging systems. In many applications, LEDs may be operated in pulse mode, where higher instantaneous optical output can be achieved during short durations compared to continuous wave operation. Pulse width and duty cycle then become important engineering considerations because junction heating ultimately affects optical stability, efficiency, and long-term reliability in lifetime. In multi-die architectures, independently addressable channels allow different wavelength groups to operate independently, supporting programmable illumination sequences and adaptive spectral control. These capabilities are particularly valuable in applications such as fluorescent imaging, high-speed imaging, PCR, multimodal biomedical instrumentation, all where timing, precision, and optical consistency are very important. Many biomedical illumination systems share common underlying engineering principles while being optimized for different optical delivery methods, wavelength requirements, and imaging modalities. The same core architecture concepts, including multi-channel LED integration, optical collection efficiency, thermal stabilization, and electronic programmability, can be adapted across a wide range of biomedical and life science applications. And what you see here in front of you is a sample of some of the biomedical instrumentation that we produce at IOI. Real-time PCR systems often require compact, multi-wavelength illumination, capable of selectively exciting multiple fluorophores with high stability and repeatability. Real-time PCR instrumentation is a good example of how many of the engineering concepts we discussed earlier come together within a practical biomedical system. These systems require compact illumination sources capable of exciting multiple fluorescent markers used for DNA analysis and pathogen detection. In this example, the compact LumiBright LED light engines are used to support multiplexed fluorescence measurements in real-time PCR systems for food safety. Multiple independently controlled wavelength channels allow different fluorophores to be excited sequentially during the measurement cycle, while maintaining stable optical output and precise timing control. Compact multi-die LED designs are especially useful in these instruments because space is often limited, and optical coupling efficiency directly affects fluorescence signal strength and measurement sensitivity. High-speed electronic control also enables rapid wavelength switching and synchronized detector operation during fluorescence acquisition. Some biomedical and life science applications require controlled illumination over larger fields rather than just highly confined optical excitation. While some applications, such as real-time PCR, require compact localized excitation, other biomedical systems benefit from larger illumination fields and adjustable working distances. This type of projected LED illumination system is designed for applications requiring uniform excitation over broader areas while maintaining spectral flexibility and high optical intensity. Focusable projector illumination can be particularly useful in fluorescence imaging, cell analysis, tissue studies, and other biological imaging applications where illumination geometry and field size may vary depending on the sample configuration. Multiple projected illumination modules may also be combined, as you see here in this illustration, or spatially superimposed to increase excitation intensity or expand the illumination field, but while still maintaining spectral flexibility and uniformity. In this example, independently controlled wavelength channels spanning ultraviolet, visible, and near-infrared regions can be combined or operated separately depending on the imaging or excitation requirements. The ability to electronically select these wavelengths also enables flexible fluorescence excitation strategies and dynamic imaging sequences without requiring multiple independent light sources or mechanical switched filters. Uniformity is another important consideration in large area excitation systems because spatial non-uniformity can directly influence imaging consistency and measurement repeatability across the illuminated field. Optical designs with homogenizers and appropriate imaging can provide uniformity better than 98%. And for our next topics, I would like to turn over the presentation to our CEO and my trusted colleague, Dr. Tom Brughlacchio.
Well, thank you, Karen, for that comprehensive introduction and review of illumination technologies. I'll share my screen. Okay, let's see. Some biomedical imaging applications require both broadband anatomical visualization and highly flexible multispectral excitation within the same illumination system. While projected illumination systems are useful for large area excitation, many biomedical imaging and tissue analysis applications require fiber-coupled delivery combined with broad spectral flexibility. This type of multispectral LED illumination system is designed to support both conventional white light imaging and wavelength selective fluorescence imaging within the same platform. In surgical imaging and tissue studies, independently controllable wavelength channels can be used to combine visible illumination with near-infrared excitation bands for enhanced tissue differentiation, fluorescence-guided imaging, and contrast enhancement. For example, fluorescence from injected indocyanine green, often referred to as ICG dye, may be used to visualize blood vessels or monitor tissue perfusion during surgical procedures while maintaining anatomical visualization under white light illumination. ICG has also been used to locate potentially cancerous lesions due to the increased visualization and perfusion of many tumor types. You can see an example here under white light illumination and under the near IR fluorescence using ICG because of the increased vascularization. You can see what wasn't observable in the white light. Compared to conventional surgical illuminators, multispectral systems can also support a larger number of independently controllable wavelength bands spanning visible and near-infrared regions. This allows wavelength combinations to be optimized for specific fluorophores tissue characteristics, and imaging objectives depending on the specific application. As the number of LED dye and wavelength channels increase, tighter temporal stability requirements may also require active thermal control, such as thermoelectric Peltier cooling devices to maintain stable spectral output and optimize lifetime by maintaining a stable and low junction temperature of the individual LED dye. Fiber-coupled delivery is particularly useful in endoscopic and minimally invasive imaging systems where flexible light delivery and high optical throughput are critical. One advantage of multispectral LED illumination is the ability to electronically configure spectral output for specific imaging and fluorescence applications. In many biomedical imaging applications, the optimal wavelength combination depends strongly on the fluorophores, tissue characteristics, and imaging modality being used. Multispectral LED illumination systems allow individual wavelength channels to be independently controlled and electronically configured to match the application requirements. Systems can be configured from UV visible through the near infrared and even the shortwave infrared, referred to commonly as SWIR. In this example, independently controllable wave bands spanning visible and near infrared regions can be adjusted individually, combined simultaneously, or activated sequentially, depending on the imaging application requirements. This level of spectral flexibility can be particularly useful in fluorescence imaging, multispectral analysis, tissue differentiation, and other biomedical imaging techniques that require selective excitation bands. External triggering and rapid wavelength switching also enable synchronization with detectors and imaging electronics during dynamic imaging sequences. Because LED wavelength distributions and output levels can be configured electronically, multispectral illumination systems can often be optimized for specific fluorophores, contrast agents, or imaging objectives without requiring major hardware changes. That is, they are inherently configurable to meet the demands of a host of different biomedical applications. Endoscopic illumination systems place unusually demanding requirements on optical performance, color, quality, and system integration. Endoscopic illumination is one of the more demanding biomedical lighting applications because the illumination system must simultaneously high optical throughput, accurate tissue visualization and differentiation, compact packaging, and complexity with advanced imaging modes, compatibility with advanced imaging modes. One challenge is delivering high radiance through relatively small fiber apertures while maintaining efficient optical coupling and uniform illumination at the surgical field. Color quality is also particularly important in surgical imaging because subtle differences in tissue appearance, blood perfusion, and anatomical contrast may influence clinical interpretation during procedures. While color rendering index, also known as CRI, is commonly used to describe color rendering quality, CRI alone does not always fully characterize surgical illumination performance. In particular, R9 is supplemental color rendering metric that specifically evaluates saturated red reproduction, which can be especially important for accurate visualization of tissue and blood-rich structures. Adjustable CRI can also be valuable because different surgical procedures, imaging systems, and physician preferences may favor different spectral balances and tissue appearance characteristics. Additionally, modern endoscopic systems may require compatibility with fluorescence imaging and wavelength selective imaging modes, placing even greater demands on the spectral control and illumination stability. These combined requirements help explain why high-performance surgical illumination has historically relied heavily on short arc xenon lamp systems. Arc lamps provided extremely high radiance, efficient fiber coupling, broadband continuous spectrum, good white light surgical visualization, and relatively high CRI compared to early LEDs. However, the limitations of xenon lamps, arc lamps, have become more significant as imaging systems evolved and LEDs improved. Arc lamp systems are mechanically complex, generate heat, have a limited lifetime, bulky architecture, and limited electronic modulation capability, and spectral control. Integrating these performance requirements into a compact surgical illumination system requires close coordination between optical, thermal, electrical, mechanical, and systems engineering and design for manufacturing and cost. Innovations in Optics LumiScope, shown here, illustrates how many of the requirements and design principles discussed earlier can be integrated into a compact LED endoscopic illumination system, outperforming the legacy short arc xenon lamp on every metric. In high-performance surgical illuminators, optical coupling efficiency, spectral quality, thermal stability, electronic control, and compact packaging must all work together within a relatively small physical footprint. The illumination engine shown here combines independently controlled wavelength groups as indicated on the previous slide. You can see blue, white, and red. With high radiance and fiber coupled delivery designed for surgical and endoscopic applications. Compact integration becomes especially important because these systems often require high optical output, stable operation over long procedures, and compatibility with multiple imaging modes while maintaining manageable thermal loading. Thermoregulation is also critical in densely packed multi-die systems because junction temperature directly influences optical output, wavelength stability, efficiency, and long-term reliability. LumiScope can be operated in closed-loop cooling mode to maintain stable spectral and optical performance under demanding operating conditions. High-speed electronic drive control additionally enables continuous wave or pulsed operation, rapid wavelength sequencing, and external synchronization with imaging systems or fluorescence acquisition modes. LumiScope is a compact multimodal illumination system capable of supporting white light surgical visualization, fluorescence-guided imaging, and enhanced contrast imaging within a single integrated platform. Unlike lamp-based systems, the LumiScope is compact, has a flexible spectrum, and does not require filter wheels, shutters, or moving optics. There is less heat generation, no bulb replacement, and minimal output drift over time. It has a significantly longer lifetime and high-speed pulsing capability in comparison to legacy short arc xenon systems. Modern LED illumination systems can now combine high-quality surgical white light visualization with fluorescence-guided imaging within a single integrated platform. Recent advances in high-radiance LED illumination systems now allow many of the traditional advantages of xenon illumination to be combined with programmable spectral control and multimodal imaging capability. In this example, broadband white light illumination is combined with independently controlled visible and near-infrared wavelength channels to support multiple imaging modes within the same system. Note the additional narrow spectrum VCSEL output in the excitation band of ICG near 800 nanometers. Additionally, near infrared output is used to visualize through blood and tissue to some extent due to the lower absorption and scattering coefficients of both blood and tissue in the spectral region. High CRI and high R9 performance are particularly important for surgical visualization because accurate reproduction of red tissue contrast and blood-rich structures may influence anatomical interpretation during procedures. Adjustable correlated color temperature also allows illumination conditions to be optimized for different endoscopes, imaging systems, and position preferences. Independently controlled wavelength groups can additionally support fluorescence-guided imaging, vascular visualization, tissue differentiation, and enhanced contrast imaging modes depending on the clinical application. The spectral distribution shown here illustrates how broadband white illumination can be combined with additional wavelength bands to support both anatomical viewing and fluorescence imaging within the same illumination platform. In some imaging modes, fluorescence from injected ICG dye may be used to visualize blood or tissue perfusion, while white light illumination continues providing direct anatomical visualization. Fiber-coupled delivery remains particularly important in endoscopic systems where compact integration, and high optical throughput are required. Although LEDs provide many advantages, matching the performance of pulsed xenon illumination systems has historically required overcoming several major engineering challenges. Pulsed xenon arc lamps remained dominant in many biomedical illumination systems for years because they provided a unique combination of extremely high radiance, broadband spectral output, and efficient fiber coupling from a very small source size. Replacing that performance with solid-state illumination systems has required solving multiple optical, thermal, and electronic challenges simultaneously. One major challenge is radiance. Xenon arc lamps generate extremely high brightness from a small plasma source, making them highly effective for coupling light into small numerical aperture fiber bundles commonly used in endoscopic systems. The difference in instantaneous radiance between arc lamps and LEDs can be orders of magnitude. Pulsed operation introduces additional complexity because biomedical imaging systems may require very high instantaneous optical intensity together with precise synchronization and stable temporal behavior. In LED systems, high current pulsing can introduce thermal shock, junction stress, efficiency droop, and wavelength shift if thermal and electronic designs are not carefully managed. Maintaining stable spectral output during rapid pulsing is also particularly important in fluorescence imaging and multimodal imaging systems where timing accuracy and wavelength stability directly influence imaging performance. Another challenge is reproducing broadband surgical white light illumination while simultaneously supporting fluorescence imaging and wavelength selective imaging modes within the same illumination system. Solid-state LED replacement of pulse short arc lamps remains one of the most challenging applications. Only through combining all the technical advancements at our disposal, including overdriving LEDs, patented light recycling, optimized optical systems to efficiently combine multiple wavelengths into the fixed étendue of the fiber bundle, thermal management, and high-speed, high-current drivers, are we only recently able to start to approach the performance of pulse short arc lamps for some applications. One advantage of LEDs over arc lamps is their ability to operate at significantly higher duty factors and frequencies, which can help make up some of the ground. Another advantage is the independent spectral control. Only recently can many, but not all, applications for short arc xenon lamps be replaced by solid state systems. High-speed LED illumination is most valuable when illumination must be synchronized with image acquisition, wavelength switching, tissue motion, or time-resolved fluorescence measurements. Examples include fluorescence microscopy, multispectral imaging, endoscopy, fluorescence-guided surgery, flow cytometry, shown in the images here, retinal imaging, and fluorescence lifetime imaging. With respect to high-speed imaging, peak optical power is only one parameter. Frame rate and repetition rate matter as well. LEDs enable fast repetition, programmable timing, and spectral flexibility. The engineering trade-offs are changing rapidly as LED radiance and pulse drive systems improve. Although xenon flash has very high pulsed energy delivered on the microsecond timescale, LEDs can compensate at the system level with higher repetition rate, synchronization, wavelength optimization, and minimal jitter. At Innovations in Optics, we optimize a given system by incorporating world-leading technologies developed over the last 3 decades with over 80 domestic and international patents to draw from, as well as continued advances from our research and development group. Biomedical imaging systems are increasingly moving beyond conventional white light visualization toward multimodal and spectrally driven imaging approaches. One of the major trends in biomedical imaging is the transition from conventional illumination systems designed primarily for visualization toward imaging platforms that support both visualization and analytical imaging simultaneously. Increasingly, biomedical instruments are incorporating fluorescence imaging, spectral imaging, molecular imaging, and quantitative tissue analysis with the same imaging methodology. Fluorescence-guided surgery, for example, is becoming more widely used for applications such as tumor margin visualization, vascular imaging, perfusion monitoring, and targeted molecular imaging. Additionally, multispectral and wavelength selective imaging techniques are being explored for the improved tissue differentiation, contrast enhancement, and quantitative tissue characterization. Another important trend is the growing integration of compact and portable imaging systems for point-of-care diagnostics, minimally invasive procedures, and distributed healthcare applications. Advances in software-controlled illumination, detector technology, and real-time image processing are also enabling more dynamic imaging approaches in which illumination conditions can be optimized during acquisition depending on the imaging mode or analytic objective. More recently, AI-assisted imaging and computational imaging workflows are further increasing interest in spectrally programmable illumination systems capable of generating controlled and repeated imaging conditions for advanced imaging analysis. One major shift in biomedical imaging is the transition from fixed illumination systems toward dynamically configurable illumination approaches that can adapt to different imaging tasks and analytic objectives. Historically, changing spectral conditions often required mechanical filter wheels, optical switching hardware, or separate illumination subsystems designed for individual imaging modes. Modern electronically controlled LED and VCSEL illumination systems now allow wavelength selection, spectral balance, pulse timing, and illumination sequences to be adjusted directly through software control. This allows imaging conditions to be modified during acquisition based on tissue characteristics, fluorescence response, imaging depth, or analytic requirements. Programmable illumination also supports quantitative imaging techniques that depend on stable and repeatable spectral conditions for computational image analysis, image normalization, and machine learning-based interpretation. Electronic spectral control can additionally reduce dependence on moving optical components, simplifying system integration while improving switching speed and operational stability. As spectral imaging, molecular imaging, and computational analysis continue advancing, illumination systems are evolving into actively controlled components of the overall imaging and analytic platform. Several emerging imaging directions are expanding the role of advanced illumination systems within biomedical imaging, image-guided procedures, and spectrally engineered solutions. One area receiving substantial attention is shortwave infrared, or SWIR, imaging, where long wavelengths may provide improved image depth, reduced scattering, and additional tissue contrast information compared to conventional visible imaging approaches. Researchers are also exploring hyperspectral and multispectral imaging techniques for applications such as tissue classification, perfusion monitoring, oxygenation analysis, and tumor margin visualization. In robotic and image-guided surgery, fluorescence imaging systems are becoming more tightly integrated with navigation, visualization, and analytic imaging subsystems to support real-time surgical decision support. AI-assisted imaging and computational analysis are also increasing the importance of stable and repeatable spectral illumination conditions for quantitative image interpretation and machine learning-based tissue analysis. Continued miniaturization of LEDs, VCSELs, detectors, and electronics is enabling more compact and portable imaging systems for minimally invasive procedures and point-of-care diagnostics. Beyond visible and near-infrared imaging, UVA, UVB, and UVC LEDs are also opening opportunities in areas such as fluorescence excitation, phototherapy, sterilization, pathogen reduction, and specialized biomedical instrumentation. More broadly, advanced illumination systems are helping biomedical imaging evolve beyond conventional visualization toward increasingly quantitative, spectrally selective, and information-rich imaging platforms. As biomedical imaging systems evolve toward more spectrally selective, multimodal, and analytic imaging approaches, illumination systems are playing an important role in overall imaging performance. Throughout this webinar, we looked at how optical coupling, radiance, spectral control, thermal management, electronic drive architecture, and wavelength programmability interact with modern biomedical illumination systems. High radiance LED and VCSEL technologies now support imaging approaches that combine white light visualization, fluorescence imaging, spectral analysis, and computational imaging techniques within unified platforms. Achieving stable spectral output, precise timing control, and efficient thermal management remain especially important in demanding biomedical imaging applications such as fluorescence-guided surgery, endoscopic imaging, and multispectral imaging systems. More broadly, illumination systems are evolving beyond passive light sources toward actively controlled subsystems integrated directly into overall imaging platforms, directly influencing image acquisition, analysis, and image-guided procedures. Ultimately, high-performance biomedical imaging illumination depends on coordinated optical, thermal, electronic, and spectral engineering across the entire imaging system. This pyramid represents the stable foundation of a user-friendly and cost-effective illumination system characterized by high performance and high reliability for a given application. The top of the pyramid indicates the critical nature of starting with exacting requirements. In some cases, a given customer may need some assistance in defining exactly what the illumination system must accomplish and how it should integrate at the system level. Innovations in Optics takes the holistic systems level approach to understanding and optimizing for a given application across the many engineering disciplines. Only by fully understanding system level requirements will an optimal system be developed. Thank you. And I will now turn it back to Haley.
All right. Thank you, Thomas and Karen, for that great presentation. We now have time for a few questions before we wrap up. If you haven't already, please type your questions and/or comments into the chat box. Okay, the first question I have here is, what are the biggest engineering challenges in designing a high-performance biomedical illumination system?
Okay, I'll field that one. One of the most critical steps, as just mentioned, is clearly understanding the customer's requirements, which is often overlooked. In many cases, we help define the system level specifications because illumination performance is tightly coupled to detector, optics, image modality, and measurement objectives. Also, it's important to consider all aspects of the design, optimizing optics, thermal management, electronics, spectral performance, packaging, reliability, and cost. So increasing optical power raises junction temperature, which affects efficiency, wavelength stability, and lifetime. So improving spectral flexibility often increases system complexity. Many of the performance metrics are independent, so improving one parameter may negatively affect another. As a result, successful designs often require multiple iterations across optical, thermal, electrical, and mechanical disciplines before an optimal architecture emerges. At IOI, illumination is treated as a complete system problem rather than simply selecting a brighter emitter, which is reflected in our LumiBrights, LumiScope, LumiSun, and others.
Okay, great, thank you. The next question I have here is, how do you maintain spectral stability when using 10, 20, or more wavelength channels?
Karen, you're muted. You're muted, Karen.
I suppose I need to unmute myself. All right, so that's a very good question. So we've dealt with systems with hundreds of LEDs to manage, actually. For example, our solar simulators. And each LED wavelength has unique behavior, right? Thermal, efficiency characteristics, aging rates, binning variations. Maintaining stability for all of those requires accurate current control. So that's representative in very efficient electronic designs. Thermoregulation. We don't want the junction temperature of the LED dye to get too hot. Calibration procedures, and often, as Tom mentioned, active feedback and closed loop control. And as the LED dye count increases, maintaining spectral balance becomes more difficult. It's a significant system level engineering challenge. Becomes even greater over the lifetime, which is a huge consideration, right? Different wavelengths age at different rates, and they degrade differently with use. Long-term spectral stability requires considering all of that, temperature-dependent behavior and all the aging effects for each individual dye. In systems that we work with, highly programmable illumination systems, individually controlling wavelengths, etc., software-controlled channel balancing can be used to compensate for these changes and to preserve the desired spectral output, so we maintain accuracy and precision throughout the entire lifetime of the instrument.
Okay, thank you. The next question I have here is, how difficult is it to achieve high CRI, strong R9 performance, and high optical power and endoscopy? And can you elaborate on R9 and why it matters?
I'll take this one, if you don't mind, Tom.
Okay, go ahead.
Then I'll give you the next one. I don't know what it is, but I'll give it to you. Let's see. So, yeah, this is kind of a fun question. It's one of the more demanding biomedical illumination problems. And whoever asked this, you're smart to consider both CRI and R9. Surgeons require accurate tissue visualization, particularly in blood-rich structures. I think Tom touched on that. So it's important to realize that high CRI alone is not sufficient. Okay, R9 performance is also important. And frankly, there's not a lot out there in the endoscopy world for illuminators that addresses that. Maintaining the color quality while delivering a high radiance through a fiber bundle requires careful spectral design and thermal stabilization. For example, the LumiScope that we presented, it was developed around all of these requirements. To answer your question about what R9 is, R9 is measured. It measures saturated red color rendering. So in surgical imaging, as an example, physicians frequently evaluate vascular structures. They look for perfusion, and they're working in a blood-rich environment, right? A light source may have a high CRI, yet still render red tissue poorly if R9 performance is weak, which it frequently is. This is why advanced surgical illuminators evaluate both CRI and R9. So there's a trade-off, right, between maximizing the luminous efficiency and maximizing color quality. Many of the high-efficiency white LEDs have excellent output, but they provide relatively weak deep red content. So surgical illumination systems like IOIs frequently require additional spectral engineering. So we put additional dye in the system and we control it adequately to maintain strong R9 performance. And at the same time, we still preserve brightness, efficiency, thermal stability, and everything that you want really in a system to make it a highly accurate, precise, and long-lived instrument. So.
Okay, thank you, Karen. The next question I have here is, why are independently controllable wavelength channels so valuable?
Okay. I like that one too, but I'm going to turn that over to you, Tom.
I'll take that. That's a good question, and it really strikes at the heart of many of the IOI light engines. For biomedical applications, different fluorophores, tissues, and imaging modes often require different excitation conditions. Independent channels allow rapid electronic switching and optimization without mechanical components. This capability is central to many of our systems, such as LumiBright for PCR or LumiSpectra for multispectral imaging. Additionally, other IOI light engines beyond those in biomedical applications use independent channel control to maximize performance. For example, IOI's LumiSun solar simulator, which could be used for various biomedical applications, but it's specific to the solar industry. Dozens of independently controlled wavelength channels are used to synthesize and precisely tune the solar spectrum. That allows the user to adjust the spectral content, compensate for aging effects, simulate different solar conditions and perform specialized measurements that would be difficult or impossible with a fixed spectrum source. While the application is different, the underlying principles are the same. Independently controlled wavelength channels provide a level of spectral flexibility and control that cannot be achieved with conventional broadband illumination sources.
Okay, thank you. The next question I have here is, what are the practical limits of TEC stabilization?
You want me to take that? I'll take that.
Okay. It's like we're just about out of time here. Right?
Oh, okay. Well, I'll speak.
We're okay. No worries about the time.
There are actually many ways of providing thermal control, right? TECs certainly are very useful for maintaining the wavelength stability and spectral balance. They consume power. They generate additional heat on the hot side. They can be complex and require effective heat removal. So all of those are considerations when we're doing our designs. In higher power systems, they're often combined then with vapor chambers, heat pipes, liquid cooling, and forced air cooling. And that enables them to achieve even higher performance. And, you know, once we graduate to multispectral systems and large number of dye, individual wavelength channels often drift differently with temperature. So as I mentioned earlier, it's important to maintain stable dye temperatures. It improves the consistency, simplifies calibration, right? And reduces the amount of spectral correction that's needed over time. So TEC stabilization, it's often combined with active thermal monitoring and software compensation too for high performance biomedical illumination systems. So we consider all of that in our design. So we're experienced with all modes of thermal management analysis and also control and all types of cooling.
Okay, thank you. For the last question I have here is, how do LEDs compare with xenon flash lamps for pulsed illumination?
Okay, Karen, I'll let you take that.
Oh, okay. Let's see. Yeah, Tom talked a little bit about this, the xenon flash lamps versus LEDs. But pulsed illumination, of course, is a challenge. They generate extremely high peak power because the stored energy is released through a small plasma arc, right? So LEDs can't match that peak pulse energy of a xenon flash, but they provide other advantages like wavelength selection, pulse-to-pulse repeatability, synchronization accuracy, those types of things. Longer lifetime, certainly. So whichever way you go, whichever technology you choose, it depends on the application, right? It depends on choosing the xenon versus LED. Depends on whether it's limited by peak pulse energy or overall imaging performance. LEDs can compensate for it to a certain extent by using multi-dye arrays. We do efficient optical coupling, synchronization with image sensors, etc. And in some biological imaging systems, the critical parameter is not the peak brightness of the source anyway. It's the number of useful photons collected during the camera exposure window. So it's not as stringent requirement to use xenon for the pulsed illumination. So that's one reason LEDs have continued to successfully replace xenon in a lot of applications. But you know, xenon has its place. There are certain applications where it's warranted.
Okay, thank you. If we don't get to your question today, don't worry. We'll follow up with you via email. And if you think of something later, feel free to reach out to us at webinar@photonics.com. Before we go, I'd like to thank our presenters one last time, Thomas and Karen, and all of you for joining us for Engineering Tunable Multi-Wavelength LED Illumination for Biomedical and Life Science Instrumentation. This webinar was presented by Innovations in Optics and hosted by Photonics Media. Thank you all so much.
Thank you, everyone.
Thank you, Haley.